Yeah.
Let's do this. Okay. So, on Monday I was talking about if you have a triangle, right? Okay, so say you have, let's call this the initial side. Okay, and we're just going to be thinking about angles. And I'm going to have an angle that rotates open.
Okay.
Okay, so it's going to, like here. Going to go from here to here. Cool. So this is going to be called the terminating side. To make things easier, on coordinate axes, the initial side is always going to be this positive x-axis. So it's always going to start at the origin and move away this. Okay? So we'll always have the same beginning point, and then the terminating side is what we're going to be looking at. Let me just have some. Okay. So when we're looking at this angle can open, anywhere. It can rotate. It can rotate to here, or it could rotate like this. Does that make sense?
But then wouldn't that make like way more than a triangle?
Well, not necessarily.
Or are we just talking about at how many degrees it needs to rotate to get to that point?
Exactly.
Or radians, whatever. I see radians in there somewhere. So.
Yes. So to find, these are called coterminal angles. Okay?
So they're not the same angle, but they're in the exact same place.
Exactly. Yes. And the only difference is that one of them is exactly 360 degrees bigger than the other. Okay? But it doesn't have to be just 360. It could be, like, what if we rotated this way?
Be.
Like this. That is a negative angle. So how many degrees would that be? Well, if this is a 45 degree angle, so you always start here, and that's 0, that would be negative 45. Does that make sense? But negative 45 would be the same thing as 315. Is this,
okay,
how do you feel with these concepts? Okay, good. So, the idea of angles having their initial side locked here and then rotating open gives us this picture of a circle. So, if we have an angle that starts here and rotates open all the way, let's pretend that looks better.
Let's pretend that looks better.
Okay, until it gets all the way back to its starting point. Okay, that is 360 degrees. But on Monday I kind of said 360 degrees is just a convention. Some dude in ancient Babylon picked 360 because it was convenient. But there's not really any mathematical foundation for why there are 360 degrees in a circle. Or why we take a circle and divide it up into 360 equal parts and call each one of those 1. Does that make sense? So what if we made this radius be 1? So this point right here is 1, 0. Okay? So that means if we were to look at this and think about the circle that is created by an angle rotating all the way around until its initial side and its terminating side are the same, then what would the circumference of that be? Well, the circumference is 2 pi r. So we're just going to plug in r as 1. So the circumference here is 2 pi times 1, which is just 2 pi. So a radian is defined as the angle that subtends an arc.
Subtends an arc?
Creates this arc right here. Does that make sense?
Okay.
Of 1. So when we're talking about radians, we're talking about what portion of the circumference it's like cutting off. by being this far open.
But doesn't that mean that radians wouldn't have any consistent basis because of if you scaled the circle up and down, that would change the amount that each radian
It would.
is?
So let's pretend the circle's smaller. Okay. What we've done is we've decreased the radius here, right?
Right.
But this also decreased.
Yeah.
And it decreased proportionally, so that the radius would still be equal to this arc subtended here.
Right.
And this angle hasn't changed. I haven't moved anything about the angle. I only changed the size of the radius.
Mm-hmm.
So it's proportional.
But
as it zooms in and out, the angle itself would stay the same, and the length of that arc and the radius would change proportionally.
I mean, though, like, here, wouldn't one unit on this circle, if this is one of some unit, wouldn't that same unit look something like this on that circle? Like bigger?
It
so
would.
the radian would be bigger?
No, because if that we took this length and we drew it here, that would not be 1 radian anymore. That would be bigger than 1 radian.
But you said the radian is based on whatever arc subtends 1.
What? So, a length of 1 when the radius is 1. So 1 radian is equal to whatever angle is necessary to create an arc that has the same length as the radius. In other words, a different way to think about it is...
Oh, an arc that has the same length as the radius. Mm-hmm. And that is...
1 radian.
Okay, the angle required to make an arc that is the same length as the radius is a radian.
Yes.
Gotcha.
Okay. So, the maximum possible radians, till we get back to here...
That's why it's scalable.
Yes. Is 2 pi.
Because it's a ratio of, like, the arc, right, and the radius that stays the same.
Yes.
Okay.
So we always make it convenient for ourselves and make the radius 1, because that is the easiest number to work with. Okay? So there are 2 pi possible radians to go from here to here until you start to repeat yourself. And then, I feel like there's a hair on my arm.
2 pi possible radians.
Right. So 2 pi radians equals 360 degrees.
So this is pi over 2 is 0 degrees.
But pi over 2 is 90 degrees.
90 degrees? Where's... Oh, that's 0 degrees. Right there. Okay.
So, let me draw a new angle.
Okay, yeah, I see. So this is 2 pi is going all the way around.
So, okay. So, remember that 2 pi is the total thing, right? So if I rotate 1/4 of the way, 1, 2, 3, 4, that's going to be 2 pi divided by 4, which is pi over 2. So this angle right here is pi over 2 radians.
From horizontal to vertical angle? Okay.
Just like 90 is 1/4 of 360.
So pi over 2 radians is a quarter of a circle.
Right. And then this is another pi over 2. Pi over 2 plus pi over 2 is pi.
Right.
And then another pi over 2. 3 pi over 2. And back to 0/2 pi.
Would be 4 pi over 2, which is 2 pi.
Exactly. Yes. So if we go halfway in between 0 and pi over 2, that is pi over 4. Right? Then we can also find a smaller angle, that would be pi over 6, and a slightly larger angle, that would be pi over 3.
Okay.
Okay? Now, all of these have degree equivalents, but we can think about that, and to get you familiar with radians. Like, it's kind of like when you learn a new language. You learn it by translating it first. You learn rojo means red. You don't just look at the color red and then start identifying it as rojo. You already understand red means the color red. So we can think about it in terms of degrees at first if you want to, but the goal is to move away from that and start thinking about it in terms of radians.
In radians.
Right. Degrees never go away completely because as a world system, we're too dependent on them for them to go away completely, but there's just no mathematical basis for them. Radians are much more like mathematically founded. Does that make sense?
This seems so much harder, though, to read than degrees. In my mind, because thinking of pi as an infinite decimal over, like well,
we don't usually refer to it as a decimal. It's almost always going to be in terms of pi.
Yeah, but you can't just say 2 radians. Can you?
We would usually say 2 pi radians. And 2 pi and 2 are not the same number.
Yeah.
2 radians. 2 is, less than pi, so that would be somewhere over here. The number 2 is less than 3.14 blah, 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 blah. So the number 2 would end up being somewhere over here. Does that make sense? Okay. But normally, when you see radians, there will be a pi there. And it has to do with what portion of the circle is that. So we're moving away from thinking about triangles into thinking about circles. But
triangles are still applicable no matter what.
Say we're at this point, okay? So this angle is pi over 6. We could always
create a triangle.
Okay? So, how does this go into the units? Not yet. Okay. So, if we wanted to find, we want to at first translate, we want to be able to move back and forth. We need to find out what 1 radian is equal to in terms of degrees. So this is an equation, so I'm going to divide both sides by 2 pi. Because 2 pi divided by 2 pi is 1, so 1 radian equals, and then 360 divided by 2 is 180. 180 degrees over pi. Does that make sense? This is what's called the conversion factor. So if I have, 400 degrees, okay, or let's say I have, let's do it backwards.
2 pi radians over 2 pi equals
1 radian.
1 radian.
Because everything cancels out except for the unit. So you're just left with 1.
360 over 2 pi.
The 2 and the 360 cancel out to leave you with 180.
Right.
But pi just stays as pi.
Right.
And that's it.
But why do we that's like creating a ratio of 360 to 2 pi. Okay.
Yes. So now, I have 5 pi over 3 radians. Okay? I want to know how many degrees that is. Well, for every 1 radian, it's 180 over pi. So I need to multiply that by 180 over pi to figure out how many degrees it's going to be.
So, wait, we have 5 pi over 3. And, that's just a radian.
Yes, that's a radian measure.
A radian measurement. And then we know that 1 radian is 180 over pi. So we're going to multiply that but we're already speaking in radians.
But we want to know how many degrees that is.
So we're multiplying our radians by radians?
We're multiplying our radian measure by what's called the conversion factor.
Conversion factor.
So the pi's cancel.
Okay.
The 3 cancels with this and leaves you 60. So now I have 5 times 60, 300 degrees.
Oh. So it's just a quick and easy little process to convert radians to.
That's it.
Can you go backwards?
You absolutely can. So say you start with 2 pi radians equals 360 degrees. So we want to know what 1 degree is. We're going to divide both sides by 360. This cancels out with this and gives you pi over 180 equals, this cancels out with this, 1 degree.
Oh, wait, so pi... Oh, and that's our conversion factor for going backwards.
Yes.
So if we're given a degree measure, which would
Yes.
be a number of degrees over 1,
You could think about it as over 1, sure.
then we would multiply it times that,
Right.
and we'd get
So say we
our
have
degrees, or our
15
radians.
15 degrees.
Mm-hmm.
We want to know how many radians that is. Well, for every 1 degree, it's pi over 80. So pi over 180. 180. This cancels out with this.
Mm-hmm.
And let's see, 12. So pi over 12. This is 180 degrees. Units cancel too.
So where would that fall in the circle? That'd be very small.
Right here.
Right there. Yep.
It's half of pi over 6.
Mm-hmm.
Yes.
Cool.
Excellent. Okay. So,
I'm just thinking of this in like the most common application of degrees that I know, which is a compass in the whole rail games. And I'm just thinking that'd be so hard to read a compass that was dealt in radians.
well, it becomes, when I first learned about radians, it didn't make any sense to me. I was like, why are we changing? I'm already comfortable with degrees. This doesn't make sense. Until when you get into calculus and you get into the higher applications of this stuff, it doesn't make sense to use degrees because there's just no mathematical basis for that. If you're working in radians, where everything is based on mathematically, there are 2 pi radians in a complete circle because that is the circumference.
So it becomes the most useful in higher math, whereas degrees are maybe easier to read for quick and simple applications.
Only because you're familiar with degrees. If we taught children
How to read radians.
and never degrees, they would think that degrees were clumsy, awkward, and large. Like, why? And obscure. Because where does that come from?
Right.
360 degrees in a circle just because some dead guy said so? Not because there's any reason? So now I find degrees to be clumsy, awkward, and too large. Like, why even bother?
Okay.
Okay. So you can make a triangle out of any of these angles, like here. So you have this angle going from here to here. If we want to use our trig functions on that angle, we would draw this line like this to the nearest x-axis, and we would just have an upside-down triangle.
Oh.
Okay?
Okay.
So, I'm going to go ahead and teach it to you anyway. All right, so
the triangles aren't really going to... I'm thinking if we did a triangle that was that 90 degrees, how do we do that? It's just 90 degrees and the corner is right there.
Yeah, it's just the straight line in that case.
Oh.
Okay. So, this angle right here, let's say this is 180 degrees or pi radians, and then we've rotated out another, say, pi over 4. So this would be 5 pi over 4 radians, okay? So the whole big thing is 5 pi over 4. But if I draw a triangle just to here, this little angle is pi over 4, because that's how far away from this it is. Does that make sense? So, I can use my trig functions. So if I'm doing like opposite over adjacent, or opposite over hypotenuse, and that's sine. The sine of pi over 4 will give me the ratio of this over this. That's the same for pi over 4 as it is for 5 pi over 4.
I'm kind of lost.
We can't draw a triangle with that large of an angle.
Right.
So what we're going to do is draw a smaller triangle just to the nearest x-axis. Okay? And we can do all of our trig functions in this right triangle because all the trig functions are based on right triangles. So I already told you we like to make the radius be 1 so that it's convenient. So say this is 1. This is our y value. This is our x value. The sine of pi over 4, only looking at this triangle, okay, is equal to opposite over hypotenuse, so y over 1, which is just y. Does that make sense so far?
Opposite over hypotenuse. Right.
And the hypotenuse is 1 because the radius is 1, so no matter where it rotates, it's equal.
So the sine of pi over 4 is y.
Yes. Okay. So,
so much.
whatever,
Feels like a lot.
whatever the sine of pi over 4 is, which I could tell you what it is, but that's not the focus here. This is a coterminal angle. This right here looks the same as if we had started here and rotated out. So even though this is an acute angle, because it's less than pi over 2, and this is an obtuse angle, because it's greater than pi over 2, their trig functions result in the same answer. Does that make sense?
Not fully.
So we can't do the trig functions on an angle that we can't draw a triangle out of.
Okay, right.
So what we're going to do is draw a triangle just by making a straight line. It's either going to go up or it's going to go down, depending on where it is.
Mm-hmm.
And then we can draw like a mini triangle.
Oh, I think I remember this process.
So, and then we can do our trig functions using the 3 sides of our little triangle that we just drew.
Mm-hmm.
And those trig functions, whatever the results of those are, the outcomes, those are the same exact ones as the larger angle.
Okay.
So if we're finding the sine of 5 pi over 4, the technique is to graph that large angle, but then to draw a smaller triangle using the x-axis and that angle.
Mm-hmm.
And you just use your regular trig functions, SOHCAHTOA, sine is opposite over hypotenuse, just to find those. This, compared to this, is called a reference angle. Because the angle itself is this 5 pi over 4.
Mm-hmm.
But we're going to be using this, the smaller angle to get our trig function values. And they result in the same answers. So we're doing our math on this
How do
one.
they result in the same answers, though? Do you have to do an additional operation? Like,
No. As everything is rotated. So it doesn't matter if our triangle is here or if we've rotated it out here.
Mm-hmm.
Everything
So that's just taking the same triangle and moving it all the way around.
Mm-hmm.
I don't see how that could work with anything but 45-degree angles.
But, okay, so...
Again, I'm thinking in degrees.
That's okay. So all this is okay, so I can erase this?
I guess, yeah.
I'm going to draw something very similar to it, but just... Okay. So. Use orange. Okay. So. I want, starting here, here's my initial side of an angle. And it's rotated out to here. If I drew a triangle back to my starting point, it's not a right triangle. My trig functions won't work. Does that make sense?
Mm-hmm.
So what I'm going to do instead is draw a straight line from my end point to the x-axis. That does make a right triangle.
Mm.
So far, so good?
Endpoint to the nearest x-axis.
Yes.
Okay.
Okay.
So that means we... Oh, I see. So, like, the way you drew it, that means those corner angles are going to be the same, right?
This and this?
Yeah. Are those always going to be the same?
No.
It just looks really close right now then, huh?
But this angle and this angle are supplementary angles.
So we can use that.
Meaning, if you add them together, they make a straight line.
Mm-hmm.
Right? So, we are going to use this angle right here, call that theta, instead of this larger angle, which we could call alpha.
Okay.
And those trig function values will be the same. You can either memorize what they are for the larger angle, or you can draw your reference angle and actually calculate them using right triangle trigonometry. So the sine of this is this over this.
Wait, which thing specifically?
Okay, so there's, let's call this one y. This is
The
our
sine of theta is y over hypotenuse.
right, which we've said is 1.
Mm-hmm.
So the sine of theta is the same thing as the y coordinate.
Okay.
So this point right here is xy. Or negative xy. Okay. So the cosine of theta, which is adjacent over hypotenuse, is x. Stick with x, not anything complicated. X over the hypotenuse. So that's adjacent over hypotenuse. But
Cosine is x.
right, so the the hypotenuse is 1. So x divided by 1 is still just x. Okay? So if we're looking at a circle and the radius is 1, to find any of our trig functions, sine or cosine, anywhere of any angle, all we need to do is look at the point and find those coordinates. The x is the cosine and the y is the sine.
Oh. And that's to find what? The
This-
coordinates are find.
The sine and cosine of the angle.
Okay.
So if I had an angle, I had this angle. Okay. Right there. And I know this point. Let's call this point rad 2 over 2, rad 2 over 2. Okay? I know that referring to this angle right here, the cosine of this angle is rad 2 over 2. The sine of this angle is rad 2 over 2. Even though I don't know what that angle is, if I drew a triangle and I actually calculated it out, my y-coordinate would be my sine, and my x-coordinate would be my cosine.
Mm-hmm.
Does that make sense? Okay. Good.
Then we can use those to find everything else we need.
In fact, there is a circle called the unit circle. And it's called that because the radius of that circle is 1 unit. So the unit circle. Does that make sense?
Okay. 1 unit of whatever.
Yeah, on a grid. So it looks like this, okay? And it has 3 angles in each coordinate, in each quadrant, labeled out. And it tells you the xy coordinates for everything. For all these points. And those xy coordinates are the sine and cosine of every possible, of all these major angles. So that if you memorize it, like I was referencing on Monday, is very helpful once you get up to calculus. Like I know offhand, the sine of pi over 3 would be 5 over 3, I said? Is going to be negative rad 3 over 2. I could draw a triangle. Well, actually, it would be. It would look like this. This is theta. And I could find opposite over hypotenuse based on theta being 5 pi over 3. Does that make sense?
I think so.
Okay, I don't want to move too fast, so let's just pump the brakes a little bit. Okay. So.
I'm feeling a little bit lost, you know?
So let's not push it, let's just stop right there and explore the things that we've done so far by doing some problems.
Okay.
Okay, and taking it slow. Okay. Okay, so that's good for today. Let's do homework. And as we're working through the problems, we'll do them with you so that you can really see more. The only other thing I want to mention, because the book is going to go more in depth about properties of all of these types of things. You'll learn those as you are exposed to them. If you, referencing the circle, okay? If you have an angle right here, this is your angle. This arc length can be found by finding what portion of the circumference that is. Does that make sense? Now, to find out what portion of the circumference that is, we need to know how much it's been rotated out. Because if it's been rotated all the way around, that's the full circumference. Mm-hmm. So the angle, this one right here, is very important to finding that. So there's a formula, and the angle is involved. So arc length, which is S. S is the arc length. It's equal to R, which is the radius, times theta. Theta being the angle.
Radius times theta.
Mm-hmm. Is the length of this arc.
Okay, so we just defined S as the arc length.
Yes. And then if we want to define the area of this sector that's created, this portion of the circle, that's equal to 1/2 r squared theta.
Isn't part of that the area of the triangle?
It's related to the area of the triangle, isn't it?
Except we have to deal with one side being an arc.
It looks right. It looks like a triangle, except there's this extra curved portion there, and that's where the angle comes into play.
Okay. Oh, so like 1/2 r squared would just be a triangle, but then when we also multiply it by theta, that adds the extra part that we need from the curve.
Mm-hmm.
Okay.
Okay, that's the only thing I want to mention. Homework time.
Okay.
Okay.
Too much.
Ask me with questions, Sam.